Thermal properties of matter. Topic: Thermal expansion. Consider a vessel containing warm water. We have a partially filled balloon, a partially inflated balloon. When this balloon is brought and immersed in warm water, we can see that the balloon starts growing, meaning the balloon expands. Similarly, when a mercury thermometer is put in slightly warm water, the mercury level rises. And if we take out the thermometer from the warm water, the level of mercury falls again. So, why it happens? That is, most substances expand on heating and contract on cooling. In case of solids, metals expand more. We might have seen that sometimes sealed bottles with metallic lids are so tightly screwed that one has to put the lid in hot water for some time to open it. When we put the lid in hot water, the lid is made up of metal, so it expands more compared to the glass. So, this would allow the metallic lid to expand more, thereby loosening it to unscrew easily. A change in the temperature of a body causes change in its dimensions. The increase in the dimensions of a body due to the increase in its temperature is called thermal expansion. The expansion in length is called linear expansion. Here you can see a material body whose length is L0 at a temperature T0. When this temperature is increased by an amount delta T, the length also increases by an amount delta L. That is, now the temperature is T0 plus delta T, that is an increment in temperature is delta T, and the length we observe is L0 plus delta L, where delta L is called the increment in length or the linear expansion produced. The expansion in area is called area expansion. Here you can see an area. Let it consider as A0, and when the temperature is increased, the area expands. The material body expands to another value, say A0 plus delta A. The expansion in volume is called volume expansion. Suppose we consider a cube of volume V or V0, and if the temperature is increased, then you can see that the volume also increases to another value, or the increment in volume, say delta V. So, the new volume will be V0 plus delta V. Solids can expand in one dimension, that is linear expansion. Solids can expand in two dimension, which is called superficial expansion or the area expansion, and it can also have a three dimension. It can expand in three dimension, which is called volume expansion. While liquids and gases usually suffers change in volume only. Now let us see what is linear expansion. When a solid is heated and its length increases, then the expansion is called a linear expansion. It is seen through experiments. In solids, for a small change in temperature, say delta T, the fractional change in length is directly proportional to delta T. So, what is fractional change in length? Change in length to original length. So, it's a ratio, change in length to original length. If delta L is the change in length and L being the original length, then we have delta L by L, which is the fractional change in length, is directly proportional to delta T, where delta T is that small change in temperature. That is, delta L by L is equal to a constant alpha into delta T, where alpha, the proportionality constant, is called coefficient of linear expansion or linear expansivity. Metals expand more and have relatively high value of alpha. Now, area expansion. For a small change in temperature delta T, the fractional change in area of a substance is directly proportional to delta T. That is, delta A by A is directly proportional to delta T, or delta A by A equals alpha A into delta T, where alpha A called the coefficient of area expansion. Now, volume expansion. For a small change in temperature delta T, the fractional change in volume of a substance is directly proportional to delta T. That is, delta V by V is directly proportional to delta T, or delta V by V is equal to alpha V into delta T, where alpha V called the coefficient of volume expansion or volume expansivity. Alpha V is a characteristic of the substance but is not strictly a constant. It depends in general on temperature scale or temperature range. It is seen that alpha V becomes constant only at a high temperature. Here you could see a typical graph of certain material, how alpha V varies with the temperature. In small range, or when the temperature is very small, alpha V is not a constant. But alpha V reaches a constant value or almost constant when the temperature is very, very high.